Okay. Please, if you have your mic on, like if you can mute, just so I don't have like any other additional distractions, that would be great. Um, but yeah, I think it's also recording for QuickTime as well, so I think we're good there. But yeah, so let me see who has their mic on so I can mute them real quick, just because it is kind of loud at the moment. Okay. There we go. All right. Everything's recording. Everything looks good on my end. Hopefully it looks good on your end. Okay, now we can finally start. All right, so specific heat value of a substance, amount of energy required to change the temperature of 1 kilogram of a material by 1 Kelvin. So you'll see that denoted, if you remember from Gen Chem, specific heat capacity as C in the equation Q equals mc delta T, right? C is your specific heat capacity. There's also an additional C. It's this big C, right? And that's just general heat capacity. And that would just be the amount of energy needed to change the temperature of a substance by 1 Kelvin without regard to how much, of that substance there is, like the mass of it and stuff, right? So that's why they call it specific heat capacity, because it's very specific to the amount of the substance there is. So amount of energy required to change the temperature of 1 kilogram of the material by 1 Kelvin. So little c is specific heat, and big C is heat capacity. Yeah, so little c is specific heat capacity, big C is just heat capacity. But yeah, it says water has a fairly high specific heat compared to other materials. So 1 kilogram of water must absorb or release 4,187 joules of energy to change its temperature by 1 Kelvin. And that's the same as 4.187 kilojoules, right? And that's probably the value that is more commonly associated, or that you've seen a lot more in your average like Gen Chem class. You see 4.187 a lot more than you do just 4,187. That's just because in your average Gen Chem problem, things are usually measured in kilojoules per mole and stuff like that. But like I said, joules, kilojoules doesn't matter. In this case, I think we're probably just going to be using joules as opposed to kilojoules to keep everything constant. But yeah, you might be familiar with the 4.187. 4,187, just multiplying that by 1,000. So it says most people like drinking hot drinks such as coffee at about 60 degrees Celsius. However, they are usually served at about 80 degrees Celsius. Okay. Okay. Someone had their mic on a little too loud and it was echoing in my ear. Sorry. Yeah, most people like drinking hot drinks such as coffee at about 60 degrees Celsius. However, they're usually served at about 80 degrees Celsius. Say you have 180 milliliters of a water-based hot drink. Same specific heat as water. If the hot drink is in a sealed container, right? If the hot drink is in a sealed container, how much heat must it lose before it's at a comfortable drinking temperature? It blurred up? Okay. I don't know what's going on here. One sec. Okay, is that better? All right, just one second. I'm just trying to rearrange things on my screen just to make sure that... I don't know why it keeps saying your stream is still running. We've paused this preview. Okay, all right. Anyway, yeah, so kind of continuing on from the theme from last semester, I'd like it if someone would kind of like, let me know what kind of thinking they went through when solving each part, just so it's just not me like giving answers out and stuff. So would anybody like to volunteer, kind of explain what they thought about when solving this problem? Or alternatively, like at this point, because I know it's kind of late, I could just probably go through this packet step by step without really asking for volunteers, because I don't think it's the time at this point. So what do you guys think? Yep, excellent. Yep. So if you have those 180 milliliters of water, right? If we're asking about how much heat will it lose before it's at a comfortable drinking temperature, so the comfortable drinking temperature, we said that was 60 degrees Celsius, right? But it's usually served about 80 degrees Celsius. So if we have 180 milliliters of water and we see that there's this change in temperature that we're trying to get to, going from an initial temperature of 80 to a final temperature of 60, right? So that's a drop in temperature of 20 degrees Celsius. Your change in temperature would be like negative 20 degrees Celsius, basically. This would technically be the amount of water that you would have. So go based on this equation here, Q equals MC delta T. We have to convert this milliliters, a measurement of volume, to a measurement of mass here. So grams or kilograms, and in this case for SI units is going to be kilograms. So we have our mass that we can figure out. We have this change in temperature, and we obviously have our specific heat, this 4,187 joules. So excellent. We'd use this equation because this equation, Q equals MC delta T, would be able to tell us exactly how much heat needs to be absorbed, how much heat needs to be released, etc. For these types of problems. In this case, it's how much heat must the hot drink lose before it's at a comfortable drinking temperature. So you should see a negative answer because that would indicate, a decrease in energy of some sort, right? So we have Q equals MC delta T, right? Those 180 milliliters, we can convert those to kilograms, right? So 180 milliliters, there's a conversion factor, which is, if you remember this from the density chapters and stuff, it's 1 milliliter is the same as 1 gram, right? Or you can also say 1,000 milliliters is 1 kilogram, right? Same thing. So 1,000 milliliters, 1 kilogram, right? Or kilogram per liter as well, because 1 liter is 1,000 milliliters. Anyway, what you can see here is that this will end up being 0.18 kilograms, I believe, right? So 0.18 kilograms, that's our mass. Our specific heat is 4,187 joules per kilogram Kelvin. These are the units for specific heat capacity because it's, once again, the amount of energy, joules, to change the temperature of a kilogram of the material, kilograms, by 1 Kelvin, joules per kilogram Kelvin. And then our change in temperature, so here's a quick kind of trick for this stuff. So the change that you see or observe in the Celsius scale will be the exact same that you see in the Kelvin scale. And the reason is that really the Kelvin scale is kind of like shifting the Celsius scale over by 273 degrees Celsius. That's it. That's the idea of the Kelvin scale there. And so you could, if you wanted to, just to kind of play it safe and make sure that everything works out, convert everything to Kelvin and then find the change in temperature. So you can take this 80 degrees Celsius, add 273 to it. That would be like 353, right? And then take this 60 degrees Celsius, add 273 to it. So that'd be 333, right? You can do that and then figure out the change in temperature there in Kelvin. So if this is 353 and this is 333, right? 333 and 353. If this is our final temperature minus initial temperature, right? Then 333 minus 353 will give us negative 20 degrees or negative 20 Kelvin as our change in temperature, right? Now, if you notice, 60 degrees Celsius minus 80 degrees Celsius, negative 20 degrees Celsius, right? Same exact difference there between the two temperatures, just because the Kelvin scale is merely just a shifting over of the Celsius scale. So What you can do is then just take that difference in temperature, that's negative 20 degrees Celsius, and you'll be like, okay, it's negative 20 Kelvin. So just change the Celsius to Kelvin. Or alternatively, what you can do is really just change this kilogram Kelvin to kilogram Celsius. And that's what you probably see more in your Gen Chem classes. 4,187 joules per kilogram Celsius, or 4.187 kilojoules per kilogram degrees Celsius, right? So either way, just make sure that all the units cancel out, because, I don't know if they're going to count you off for it on a quiz or exam, but definitely make sure you have your units cancel out and everything makes sense. So yeah, joules per kilogram Kelvin, because I just want to keep SI units and stuff, because everything is in Kelvin for this class. And then, yeah, and this is negative 20 Kelvin there, right? If you do all of that, multiply everything out, you should get around negative 15,073.2 joules. I think this problem was pretty much the exact same as my old homework, so I'm solid on this one. All right, any questions at all about part A for this? Or are we all chilling about this one? All good. All right, sweet. All right, I will go back to the QuickTime. So it'll say paused here for a second. I just want to make sure that everything is recording properly. Yes, okay, yep, all right. Just want to make sure the mic is on and everything, because, yeah, anyway. So, it says, this is a fairly slow process due to the low thermal conductivity of the material of the cups. To speed up the cooling, you could instead leave the lid off your drink so that some of it can evaporate. Each molecule that evaporates must gain energy to break the hydrogen bonds with all of its neighboring molecules. They receive this energy from the rest of the liquid, decreasing the internal energy of the remaining liquid and thus cooling it, right? The energy acquired by the evaporating molecules or lost by the liquid is called the heat of vaporization. So this is the energy acquired by the evaporating molecules or lost by the liquid, right? Is called the heat of vaporization. For water, it's 40,660 joules per mole, or 6.75 times 10 to the negative 20 joules per molecule, right? So if you remember from Gen Chem, heat of vaporization, and if I remember it from Gen Chem properly, basically that would be kind of the amount of energy it would take to switch phases between liquid to gas or gas liquid, right? And at that point, I believe you wouldn't be seeing a change in temperature, just a change in state. Someone correct me if I'm wrong about that, but I believe that's the case. Like I said, I'm a little rusty with this stuff, so just want to make sure that that all makes sense. Any comments about that at all? Yeah, I was saying that the heat of vaporization is just defined as the amount of energy needed to basically just switch states of matter. So it's not like this change in energy, right? The 40,660 joules per mole is not the amount of energy that it takes. Well, I guess it's not amount of energy that would cause a change in temperature. I'm saying that it would be an amount of energy just to merely change the state of matter. So like you can't plug this equation into Q equals MC delta T, but you could plug it into Q equals MC, big C, because this would be more like a heat capacity than a specific heat capacity. Sort of. And it kind of makes sense too, because if you look at the units, is joules per mole, joules per molecule. There's no Kelvin or there's no Celsius, right? It doesn't factor in change in temperature. So yeah, I believe it's just the energy required to just switch phases from liquid to gas or gas to liquid. That's why it says the energy acquired by evaporating molecules or lost by the liquid. All right, so yeah, I think we're solid on that. Yeah, I looked it up as well, and it looks, yep, we're good. Anyway, for part B now, it says, assume that 9 milliliters of your hot drink evaporates. Assume its molar mass is that of water, right? So how much energy was removed from the liquid to evaporate that amount? So you have 9 milliliters of the hot drink, right? Remember, we initially had 180 milliliters of that hot drink. So 9 milliliters is gone now. 9 milliliters has evaporated. So that's just during that evaporation stage, right? Just during that switching of states of matter. So just going from liquid to gas, 9 milliliters was removed without even changing the temperature of the hot drink, right? So we're looking at how much energy was removed just to evaporate and not like change any temperature, just to basically switch it from liquid to gas. And that's why we would factor in something like this heat of vaporization as opposed to a specific heat capacity, right? So if we're looking for that energy, right, what we can do is take that 9 milliliters of that hot drink and then convert that to a specific mass of the hot drink. So remember, once again, for that older conversion unit, 1 kilogram, 1,000 milliliters. So we should have 0.009 kilograms, I believe. Yep. And then, well, actually, let me think about it real quick. So if we want to use these like values here, like the heat of vaporization, and it's in moles, then I think it would probably be better if we don't convert to kilograms and instead convert to grams, right? From grams, we can convert to moles using molar mass. And then from the molar mass, right, we can get to how much energy we would need to remove from the liquid to evaporate that amount. So if we go from those 9 milliliters, right, we can use that specific conversion factor, which is similar to the one I explained above. So instead of 1 kilogram divided by 1,000 milliliters, we can say 1 gram divided by 1 milliliter, right? And then that is your 9 grams. So that's the mass of that water right there, right? So that's the amount of water that we have that evaporated. And like I said, when we're looking at the mass of the water that's evaporating here, the energy to remove that mass of water will just be based on one of these values here, just depending on what or how or which units you're deciding to use. If you use moles or molecules, essentially what you're going to do in the end is figure out the Q value, right? So your heat value, the amount of energy removed to evaporate that specific amount. So if we have those 9 grams, right, we can use this value here. I think that would probably be easier. We don't want to deal with any exponents here at the moment. So if we have 40,660 joules per mole, well, however many moles this is, we can multiply it by the heat of vaporization to figure out exactly how much energy, right, was removed from the liquid to get it from that liquid state to a gaseous state. And that's what the heat of vaporization is. There's no change in temperature at that point. It's just a transition period. So if you remember from Gen Chem, what it kind of looks like I can't remember exactly what the graph is called. Maybe I'm just stupid and I just forgot like the general name for it. But like there's kind of this graph that kind of shows you transitions between states of matter, right? So basically on that graph, you might have this portion here be your liquid. Here's that transition period. And then this portion here is your gas, right? This transition period is your heat of vaporization, right? At this point, like the graph basically looks at like, hold up. What did I want to say? Yes, temperature here up top, right? On the y-axis. So temperature would just be constant along that point. There's no change in temperature there. So it's just merely just a transition of states of matter at that point. So again, we have those 9 grams. And now we can convert from 9 grams to moles, right? And so remember they said this was a water-based hot drink, right? So we can convert to moles using the molar mass of water. And so 1 mole of water, right? So 1 mole of H2O basically is roughly 18 grams, right? Because you have, depending on the periodic table you use, you might see oxygen being 15.999, or, you know, that's basically 16, and then your hydrogen, each one I think is like 1.018 on some periodic tables, but 1 basically, right? So 16 plus 1 plus 1, that gives you your molar mass there. And then you can see here, right, that you will have the mole amount, and that's roughly 0.5 moles right there for your energy, or not your energy, the amount of water that you have. So there's 0.5 moles, right? Let me just move this over real quick. 0.5 moles of the water. And then we can multiply this molar amount by the heat of vaporization, 40,660 joules per mole. And that'll give us, you can see moles will cancel out here, and that'll give us the amount of energy that would be released there or removed from the liquid to evaporate that amount, right? Does anyone have that specific value calculated out? I will take your word for it, because I don't have this thing calculated. So, all right, seems that's the consensus in the chat as well, that it's 20,330. All right, so 20,330 joules removed. So I would say remove there, right, to indicate that this is a loss of energy in that case. Yeah, so you can say 20,000, excellent question, Hamida. 20,330 joules removed, or you can say negative 20,330 joules, right? You can say that that was how much energy that was removed in that case. So either one, as long as you're distinct that there's a decrease in energy in a sense, then you're good. But yeah, makes sense for B so far. Oh, sweet, people can react. I did not know that. So I see thumbs up like in the bottom left corner of my screen. See, I love this thing. Zoom was trash. All right. So that's B. So, or B1, I guess. B2 is calculate the final temperature of the drink. It's important since the amount of liquid changes. You can't use a specific heat to find its energy change. Instead, recall that the internal energy of water is U equals 6N kBT. That's equal to 6 nRT. In terms of the changing number of N of molecules or N of moles, determine Ni and Nf. Find expression. Okay. So so they want us to calculate the final temperature of the drink after those 9 milliliters were lost, right? And then factor in, obviously, that change in the internal energy of the system, right? Because we lost 20,330 joules. That would be essentially our delta U, negative 20,330 joules right there, right? So we want to basically use this equation, set it up in a way where we have specific final internal energy, specific initial internal energy, show that change, and then factor in the change in the, or factor in this final temperature here that we're looking at, right? So someone had asked this earlier. I intended on replying. I apologize for not doing so. I think someone else answered them anyway, so that's good. But N here, big N is number of molecules, little n is your number of moles, right? So if you remember from the equation PV equals nRT, this little n, that's how the equation looks like. This little n indicates moles, big N indicates molecules, right? And if you remember as well from 131, remember where we had, what is it? For the, what's it called? Shoot. I totally forgot. Degrees of freedom stuff. Remember, like we had 3 halves n kBT, right? that big N was the number of molecules there, and that's how we figured out like the total energy of a system for 131, if you remember that. Anyway, they want us to set up this equation, delta U is equal to UF minus UI, right? Well, they kind of gave us a hint here already as to how to set up each U. So we know that delta U is that negative 20,330 joules, right? That was the energy lost there for the internal energy. Now for UF, we can look at this little part right here, right? 6 nkBT. So N will be the specific amount of molecules at the beginning. So that's the 180 milliliters of water at the beginning. N initial, or my bad. Yeah, N final would be the whatever you have left over after the 9 milliliters have evaporated. N initial would be the 180 milliliters, however, whatever, amount of molecules that is at the beginning, right? So we can convert that and figure things out that way. Now, I think, once again, just for the sake of keeping things consistent, easy to kind of look at, stuff like that, if I were to use this big N, molecules and everything, then I would have to use this heat of vaporization somewhere along in the equation, right? And that would kind of throw things off. Or, well, I guess, now that I think about it, maybe, yeah, no, you don't. I don't think you need that for this part, but maybe for a different part, I think you might need it. But, yeah, because I think you only just need either Boltzmann's constant or... Oh, but wait. Because Boltzmann's constant is 1.38 times 10 to the negative 23 joules. What is it? That just should be joules per mole Kelvin as well? Or would that be different? Yeah, I think it is. Hold on. Let me just double check real quick. I think it's just joules per Kelvin. Yeah. Yeah, it's just joule per Kelvin. Yeah, no, I'm stupid. Yeah, it's just joules per Kelvin. Because that way, if you think about the equation, if this is joules per Kelvin, this is Kelvin, Kelvins will cancel out, and then you're just looking at, like, this number of molecules multiplied by the energy, like, per molecule, basically, in a sense, and then everything. You'll be able to figure out the total internal energy at that point. I'm going to use this equation, so I'll just take a decision. I'll use this equation just because we already have a specific molar value anyway, and it'll just make things a little bit easier to look at. So, U final, the way we're going to set that up is 6 little n RT F minus 6 little n RT I, right? So that's your U F, and this is your U I. 6 nRTF minus 6 nRTI, right? And then from there, we can look at the number of moles. So for final number of moles, right, it's not just the 9 milliliters or the 0.5 moles here that we figured out, right? That's how much evaporated, right? So we have 180 milliliters first. We evaporated 9. So how much do we have left over? $171. Excellent, right? So we have 171 milliliters left over here, right? So we can take the 171 milliliters kind of off to the side here and convert that to 1 milliliter, 1 gram, and then from 1 gram, 18 grams mole to figure out basically how many moles of water, because it would be the final amount would be that 171 milliliters after 9 milliliters had evaporated. Convert that to grams, and then convert that to moles using the molar mass of water. And so from that, I think you should get around like 9.5 moles, I think. Right? Yeah. And then if we use our intuition, right? Well, if we ended up, our final amount was 9.5 and 0.5 was evaporated, 0.5 was evaporated, and our final amount is 9.5, then how much did we have from the beginning? 10 moles. Excellent. So we started off with 10, 0.5 evaporated. Now we're left with 9.5, right? So that simplifies things a little bit. We now have 6 times the final amount of moles, which is 9.5 moles, times the ideal gas constant. And so if you remember from Gen Chem, once again, there's kind of a couple different values depending on your situation. Since we're not dealing with pressure or anything like that, we're not using the 0.0821 liters atmospheres per mole Kelvin, right? Because there's no pressure involved. We're going to be using 8.314 joules per mole Kelvin, right? So 8.314, I'm going to forego writing the units for now just so I can save some space. And then our final temperature, right, is what we're trying to figure out after losing those 9 milliliters. And then minus 6 times 10 moles, right? That was our initial, times the ideal gas constant, joules per mole Kelvin, times the initial temperature, right? And the initial temperature was, what was it? That 80 degrees Celsius, right? And we can convert that to Kelvin, and that's 353 Kelvin. Reason why we want to have this in Kelvin, not Celsius, is because the ideal gas constant here is 8.314 joules per mole Kelvin, right? Can't do it with Celsius there. Keep things in Kelvin. And I would prefer, like even that trick that I showed you guys up there, if this was me on an exam, my neurotic self would insist on still converting this to Kelvin, just so I know that I'm like in the right units and everything kind of matches up. But there we go. That's the equation setup. Negative 20,330 joules, right? And then from there, just mathematical manipulation to solve for TF. So, let's see here. I'll field the question. What did you guys get for TF? I think this problem is like slightly different than ours. So, yeah, so it looks like 328.7 Kelvin. Okay, fair enough. I'm not a fan of rounding, so I would keep 328.7. Yeah, I just include as many decimal places as possible. Should the answer be in 2 decimal places? Doesn't matter. 328.7 is fine. I just think that like if you have a decimal, right, I don't think that you should just kind of like disregard those decimal points and round it up to the nearest thing, the nearest value. So 328.67, 328.7 is fine. Either one is okay. But I would prefer for you to have that as opposed to 329. Once again, like if you want to risk it all, play a little game with the TAs, then that's up to you. But yeah, no, sig figs are, yeah, so you don't have to worry about sig figs for this class. If you did, I would have lost my mind. Like I would have worried more about like calculating things properly in sig figs than actually learning the physics in this class. Because like losing points for sig figs is just, that would just be stupid. Anyway, I'm just taking a look at some things here. Just because I see some people have been asking me where the session is at. Shoot. Hold up. Bear with me for a sec. All right, sorry about that. Anyway, everything making sense so far? No, we're almost done, honestly. Because the last few parts are pretty chill. All right. Oh shoot. Okay. More units again for this is 8.314 joules per mole Kelvin. Yeah, for the R value. Yep. And Kelvin for your temperatures. All right. So now for part C, it's saying we'd like to know how much of the drink itself must evaporate for it to reach the drinkable temperature. So we're just wanting to solve for the final number of particles, NF, or moles, NF, little n there. So it's kind of like a rehash of this stuff, but instead of like finding the final temperature, we're finding like the number of moles basically to get to a final temperature of that 60 degrees Celsius or that 333 Kelvin. I know it's late, but for motivation, you think this class was easier at the 131. So that's an interesting question because, like, statistically, so it's a little weird. Like, my quiz grades for 132 were trash. Like, I'm sorry, they were absolute trash. Like, I don't know if I just like had a lot on my plate at that time or what, or if I just wasn't studying properly. I don't know, but like, I just felt like the quizzes were kind of tough. Um, I will not say what I used to say to my friends about how the quizzes were structured, just to not scare you guys. But 132, it's subjective because I like electricity, I like batteries, I like circuits, I like that. Like I'm a demon at circuits. When it comes to circuits, I'm good. Like I'm so good at circuits. But I prefer 132 topics. I think 132 as a whole is just more connected than 131. 131 you have to cover a lot of topics to kind of get that basic foundational knowledge of physics. 132 is kind of more limited in how much you cover. Like as a whole, there's a thermochem section, there's an electricity section, and then there's a magnetism section. Like it's almost like three big units, and within each unit you kind of build upon your skills. Like for the electricity chapter, you start off looking at electrons, protons, attraction between nuclei, stuff like that. Then you get into batteries. Then you get into circuits. Then from circuits and batteries, you get into capacitors and stuff like that. So it's kind of building on top of each other in a way that kind of is more cohesive and makes sense. Going back to the statistically thing that I was talking about earlier, statistically, my quizzes weren't the greatest, but my exams were off the charts. Way, way, way easier exams in my opinion than 131, and that's probably mainly due to the fact that there's no multiple choice on the exam. It's entirely written, and I feel that's a lot better to show kind of what you know, explain stuff, write things down, more opportunity for partial credit, because I feel like a lot of you guys, and I've seen some of your exams, like, I'm going to be honest, like I've seen some of your exams on Gradescope, like y'all would have done 10 times better if there was no multiple choice on that section, because some of y'all aced the written portion but got completely screwed by the multiple choice. I don't know if you're able to do well on the written, it shows you not only have the conceptual understanding but also like the ability to kind of apply it mathematically. So yeah, I think this class is a lot easier than 131 in my opinion, but 131, you're kind of spoon-fed the information. The PowerPoints are there, the written homework is there, all of that's there, very easy to see and stuff like that. But for 132, in order to succeed in this class, I'm just telling you right now, choose to believe me, choose not to, choose to do this thing or not. But the readings are so incredibly crucial to this, to succeeding in this class. And yeah, if you do the readings, if you read them, they're long as hell. Like it got to a point where I'd almost like have the readings done, understand the concepts fully, but like have no time for homework because I was so like hell bent on understanding more than doing the math because I knew I could do the math. But I didn't mean to throw you guys under the bus. Like, I'm just saying, like, it's actually more of a compliment because I feel like you guys understand the concepts. It's just that I agree, like, the multiple choice, like, is kind of tough in a sense because, like, some of them will literally just test you on the ability of being able to read a problem or not. Like, if you misunderstand the problem or like or just look at an answer option incorrectly, you're done for. But yeah. Anyway. Yeah, so I think 132 is a little bit easier. But you just have to want to look for the information and be active in the sense that if you want to learn and succeed in this class, you're going to have to put in the work. So, but yeah, the readings, like, my friends wouldn't do the readings, and their success in the class was a little bit more variable. Like, sometimes they might do really bad on a quiz, really good on another quiz, right? I felt like I was consistently average on the quizzes just because there's just a lot to do on the quizzes. So I'll just go ahead and say it's like twice the amount of work in the same amount of time as 131. But if you know your stuff and if you're practicing the material as often as you can, you could literally, like, forget or not worry about the quizzes as much. And if you're able to understand everything and have practice with that, the exams should be a cakewalk for you. I remember, like, I got a couple of C's and D's on the quiz, one F I think, or maybe two F's on one of the quizzes, or two of the quizzes, yeah. But and I still made it out. Like, the exams, I won't say like my grades and stuff, but like I did extremely well in the exams. I had Dr. Espinoza. I think he popped in here for a second, like, earlier, and I was explaining, and I did not know what to do. But yeah. Okay, I've kind of deviated for a while now. I'm sorry for those that are here, like, to actually, like, do the homework, so I apologize. I'll get back on track here. I'll answer any questions you guys have about, like, the course here after we're done with this homework. So, all right. So, I'd like to know how much of the drink must evaporate for it to reach the drinkable temperature. We want to solve for the final temperature or final number of particles, NF, or moles, NF. So it says write an expression for delta U equals UF minus UI in terms of TI, TF, NI, NF, or these two. I think I'd prefer to write it with moles instead of molecules. So delta U, right? Remember, U from before, we had it as 6 little n, not KB, little n R T F minus 6 little n R T I. Right? That's it. That's the equation that you have to write down. You could write down both if you want to, one in terms of big N, one in terms of little n, but you only need one. So it says write an expression, not write expressions. So that's C1 there. C2, just like before, right now an expression for the amount of energy carried away by the evaporating molecules. So we're looking at the amount of energy carried away by those evaporating molecules in terms of the heat of vaporization, Ni and NF. Okay, so they want us to do it with the molecules now. How does this energy relate to the change of energy delta U of the remaining liquid? Use the two expressions for delta U to find NF. Damn, that's not a lot of space to do that. What was I saying? What was I going to say? So I think they specified big N instead of little n. So that's kind of inconvenient. I don't like that. But we're looking at amount of energy carried away by the evaporating molecules. So that's using the heat of vaporization. So there shouldn't be a change in temperature, right? In that transition stage. So for that amount of energy that's carried away, that's our change in energy carried away, or change in energy, right, for that evaporation. So our delta U, UF minus UI, right? And then we can see that this delta U is going to be that energy change, right? Which is like this part, basically, I think, if I'm not mistaken. More or less, just with capital N molecules instead of little n moles, right? So if we're going by this as 6.75 times 10 to the negative 20 joules per molecule, because they want the heat of vaporization and everything else to be in terms of molecules, right? So the change in the energy that we should see should be equal to that heat of vaporization, 6.75 times 10 to the negative 20 joules per molecule, right? Multiplied by the change in the molecules that we see, right? So remember here, we took that change in the number of molecules or the milliliters or whatever. So we had a change of, or evaporation of 9 milliliters, right? And that ended up being an evaporation of 0.5 moles of water. We multiplied the amount of moles of water by the heat of vaporization to figure out exactly how much energy was lost due to the evaporation of those moles of water or molecules of water, right? So essentially we're doing this again, right? Except that in this case, we want to figure out how much or how many molecules are left over after reaching that drinkable temperature. That's the idea. So we know that it started off at 80 degrees Celsius or 353 Kelvin. It ended up at 60 degrees Celsius or 273 Kelvin, right? And then what we're doing, so we have our TF and we have our TI, right? We know our initial number of molecules, or we can figure that out because we had 180 milliliters of the coffee at the beginning, right? And then what we're trying to figure out is the final number of molecules, right? So some of these, like, these are more complex sometimes than the 131 problems in the sense that you really have to understand what they're asking for. So I know that I have Ni. I started off with 180 milliliters. We can convert that to molecules later, right? NF is what they're clearly asking for, right? That's the basis of the question right there. That's what I'm trying to figure out. How many molecules of the drink do I have left over after some of it has been evaporated, right? So you can also say that, okay, well, I want to figure out how much I ended up with. If I only know how much I started with and I don't know how much I ended up with, then you can also say that I don't know how much actually evaporated, right? I don't know how much actually evaporated. And so at that point, if we go back to the setup here for this equation, 6 nRTF, 6 nRTI, if we made these instead of moles to big N as in molecules, right, we know that, actually, I'll just write the equation down at this point. So this would essentially be equal to your heat of vaporization times the change in your molecules, right? And then that's equal to 6 big NF, your final number of molecules, right, multiplied by KB, right? Because remember, for that other equation, it was 6N KBT, right? So 6NF, final number of molecules, times KB, times the final temperature, right? Minus 6Ni, the initial number of molecules, times KB, Ti, right? We know the initial temperature was 80 degrees Celsius. We can convert that to Kelvin. We know the final was 60 degrees Celsius. We can convert that to Kelvin. KB is a constant. Ni, we know how much we started off with exactly, right? We know that we started off with 180 milliliters. We're trying to figure out NF. Yeah, we're trying to figure out NF, right? And 6 is constant on both sides. For delta N, delta indicates a change. So like NF minus Ni, right? We know the initial, we don't know the final, right? Now, here's another thing too. If we want to maintain that there was a loss or a decrease, not loss, but a decrease in the internal energy. C1, the equation was this. It's going to be slightly different for C2 because instead of using moles, little n, we're using molecules, big N. But in order to be kind of consistent with the idea that there's a loss in energy, this part here is going to be a little weird. So we want to make sure that delta U is a negative number, right? We want to make sure that the delta U is a negative number to indicate that there is a decrease in internal energy, right? There's two ways you can do that. You can either say heat of vaporization times NF minus NI, in which case your final, you know that some of it's going to evaporate. So you know your final number of molecules is going to be less than your initial number of molecules. And so if this was 3 molecules and this was 4 molecules, you ended up with a negative number, right? And so that's -1, right? And then you can just multiply by the absolute value of the heat of vaporization. So you just take that negative, the decrease in the number of molecules, that negative number, and multiply it by this, and you're solid. The mistake that I made, that I remember making on this homework, right, is doing a little bit of both. And so what I mean by that is that, okay, well, previously I determined that heat of vaporization should be a negative number, right? Because essentially, like, if we're looking at, remember, I guess, well, I just, let me kind of think about that again. Yeah, so I think, so if you were to look at this and you'd be like, okay, well, when we use heat of vaporization, we added that negative sign to indicate that there was a loss of energy, right? So you might put a negative number to indicate that there was a loss of energy there, right? It says a stream is full. Hold up, so like people can't join? Hold up. Oh, won't let you view because it says it's full. That's weird. $50 max. That's not good. Okay, I'll have to figure out something out to increase the amount of people that can join. We have over 50. Damn, I did not know that. Yeah, I can. Well, yeah, we might need Discord Nitro for this server. I was not expecting there to be this many people. Yeah. It's not possible to raise it at all. Or if you have Discord Nitro, you're able to have like a higher cap. Is that the deal? No, but I think you can. I don't think anybody has their webcam on, no. But, let me try and edit the channel real quick, see if I can increase the amount of people that can be in here. I don't know if that's possible. Yeah, I'm not sure. Okay, so I will thank you for that. Great that we figured this out early on. So I will try and figure out a solution for this later. But yeah, I'll just make sure to get through this thing and have it uploaded as soon as possible. Okay, yeah, let's just get through this and upload this and hopefully it'll be in here or on YouTube before midnight. Anyway, so yeah, the mistake that I was saying that you shouldn't make is that you shouldn't have like a double negative, basically. So you can't have a heat of vaporization that's negative and then also put NF minus NI, because NF minus NI, because since there's an evaporation, there's a loss in the number of molecules, right? Because you go from having a certain number of molecules, it evaporates some of it, so you have a less number of molecules at the end. This will inherently give you a negative number. If you have two negatives, you're going to end up with a positive delta U, and that's going to throw off your entire answer. That's what happened to me. So you can either say, take the absolute value of that heat of vaporization, keep it the same there, just a positive value, and then just do NF minus NI, right? And that'll give you an automatic negative answer for delta U, and that's fine. Otherwise, you can say that this is negative heat of vaporization, and then instead of NF minus NI, you can say NI minus NF, because then this would be like 4 minus 3, right? You'd have more initial than you do have for the final, and so that's how it would kind of go. But yeah, anyway. So we can just keep it as positive. This is NF minus NI, right? And then you have your UF minus UI, 6NF KBTF minus 6NI KBTI. So if we set that up real quick, right? So that's 6 times the final number of molecules, right, which is what we're trying to figure out, times KB, so that's 1.38 times 10 to the negative 23 joules per Kelvin. I will forgo writing units for now just to save some space. TF, we know that that was 333 Kelvin, I believe, because that was the 60 degrees Celsius, right? 333 Kelvin minus 6 Ni. So we started off with that 180 milliliters of water, right? And if we convert that, right, to what was I going to say? To molecules, what should we get? I haven't had a chance to calculate. Anybody have that real quick? $180 milliliters of water, change that to molecules. That's what we're trying to get at, right? We're trying to figure out the initial number of molecules there. So someone said it's 40,648.5. Is that right? It seems really big, but I wouldn't know. Actually, one second here. If this is the same as my homework, I think this was the same as my homework. Yeah, go ahead, Matthew. Yeah. Yeah, exactly. Yep, I'm just looking for it to be in units of molecules. And I think what I got here was that if this is 180 at the beginning, yeah, this was 180. So I think it is 6.017 times 10 to the 24 molecules. That's exactly what I got. So yeah, 6.02, it kind of depends on like which values you use for your molar mass and stuff. I'm very like accurate and thorough and precise, so I use like 18.0018 grams as my molar mass for water. So it might be a little bit different, but yeah, roughly around that range, 6.017 times 10 to the 24 molecules is your initial amount. And I'll explain how you get that here in a second. So 6.017 times 10 to the 24, that's molecules times 1.38 times 10 to the negative 23 joules per Kelvin as your Boltzmann's constant. Move this over a little bit. And then Ti, that was 353 Kelvin, right? So our NF is unknown. That's what we're trying to figure out. Our Ni, on the other hand, right, that would just be the same 6.017 times 10 to the 24 molecules from before. So 6.017 times 10 to the 24. Kind of hard to see, but sorry about that. And then it's just a matter of very ridiculous rearrangement of values there algebraically. In the end, I do believe you should get the same answer that I got when I took this, is 5.77 times 10 to the 24 molecules as your NF, I believe. Roughly around that range, yeah. Once you solve for NF. I just want to make sure that, yeah, I took NF minus this large number of initial molecules, and I did all of this stuff. Yeah. It's very complex, but yeah. Go ahead, sorry. Oh wait, that's kind of weird. Use two. Use the two expressions for delta U with the correct signs to find NF. So, I mean, I'm not even gonna lie, I have no idea what they're talking about. Because we really just wrote one expression technically. It's just, I mean, unless they're telling you to like literally do this problem twice, once with moles and once with molecules. Oh. Oh, I see now. So it says, just like before, write now an expression for the amount of energy carried away by the evaporating molecules. That expression would literally just be that the delta U is equal to heat of vaporization times delta N. So like you use delta U is equal to like heat of vaporization times delta N, and then you set that equal to, like that would be your first expression, and your second expression that you would set it equal to would be the 6 NF KBTF minus 6 NI KBTI. Does that make sense? Those are the two expressions you'd use. It's kind of weird because I already like consolidated it into one expression, but yeah. And the way I got this huge number here is that I took 180 milliliters, right, times, that's 1 milliliter per gram, right? And then there's 18 grams in a mole of water, and then 1 mole is equal to 1 mole is 6.022 times 10 to the 23rd molecules. So you end up with molecules on top. So it's 180 milliliters is a gram, 18 grams in 1 mole of water, and then 1 mole of water is 6.022 times 10 to the 23rd molecules. If you solve that out, you should get that huge number. I got 6.017 maybe just because instead of using 18 grams as my molar mass, I use like 18.018, so it'll depend. But in your final answer, like that difference is so small that you still end up with right around this number of molecules. Sound good? That's an odd emoji to use to react to sound good. All right, fair enough. All right, so part 3 here is determine the percent of the drink that was lost, Ni minus NF over Ni, or little Ni minus little NF over little Ni. And they're the same anyway. So you just pick one and roll with it. And so, yeah, this is really simple. All you do is take that initial, right? That initial is that 6.017 times 10 to the 24 that I had. If you got 6.02, that's totally fine. Stick with that, as long as it matches your work. And then minus 5.77 times 10 to the 24 divided by 6.017 times 10 to the 24, right? So your initial minus your final divided by your initial, and then whatever you get there multiplied by 100 to get your percent of the drink that was lost. You should get around, like, I think what I got was like 4.15% change or something like that. Yeah, go ahead. Go ahead. Yeah, so if you use for delta U, so delta U should have right here, it should be your heat of vaporization, a positive value, times NF minus NI. NF minus NI will inherently give you a negative value because you have less water at the end than you do at the beginning. So this will end up being a negative value, and that negative times a positive will give you a negative value for your delta U, which makes sense in the grand scheme of things because there should be a decrease in energy because there's evaporation, that you've lost a certain amount of water, right? So um, in this case, the left-hand side should be negative, so make sure that's the case. And then you have 6NF kBTF minus 6NI kBTI. So 6 times your final number of molecules that we're looking for, times Boltzmann's constant, times your final temperature, which was that 60 degrees Celsius or 333 Kelvin, minus 6 times your initial number of molecules, which, like I said, is that 180 milliliters, converted to grams, go from grams to moles, and from moles to molecules. So that's the number of molecules there that you started off with, and then times Boltzmann's constant, and then times your initial temperature, which is that 80 degrees Celsius or 353 Kelvin. I think what it sounds like maybe is that you might have messed up on this part right here. You might have had a negative or a positive answer overall, and that would throw off your final answer. So make sure that you got this kind of notation there, and that you should end up with a negative for your delta U, at least on like that left-hand side. Does that make sense? Okay, awesome. Like I said, what's good about this class is that there's a lot of partial credit, like an insane amount of partial credit. Like I'm telling you, first exam that I took, I did really well on it, but there was a whole problem on the back, like the very last page. I'll never forget it because I literally had like 15, 20 minutes to do that problem, and I had no idea for the 15 and 20 minutes that I sat there in the lecture hall. I was like, dog, I don't know what to do. I don't know if I went up to Dr. Espinosa and asked, and I was like, but I just did not know what I was doing for that last problem. So I just wrote the equations down that I thought kind of like addressed parts of the problem, wrote my values. Like I knew what I was doing was wrong. I just didn't know like what else to do. So I just wrote some things down, wrote the equations, and I got like maybe 60-70% of the points that you could have gotten on that problem. Because what I ended up doing was that I got the first part wrong. Like I didn't know how to do part A. Parts B, C, D, and E, I was like, all right, well, whatever answer I get from part A that I don't know how to do, I know how I can apply it for B, C, D, and E. So I completely screwed up part A, which was like the bulk of the points. But then for the rest of it, I was like, all right, I kind of understand where I'm going. And so I got full points for the rest of the parts. I think maybe I might have messed up one other part or something like that. But the gist is that there's so much partial credit in this class that you should be solid, because you avoid the issue with the multiple choice. Um, but yeah, that's number 3. Hopefully that makes sense. And now the last, yeah, go ahead. Yeah, you can kind of simplify it in the sense that you can say like 6 kb, um, and then like NFTF minus NITI if you want to do it like that. That also works. That might clean it up a little bit. Yeah. Yep, for sure. Now this last part here, hopefully I can get this uploaded real soon, is this method of cooling down a drink still involves waiting a while. If we're impatient, we can instead add a little tap water, say at 15 degrees Celsius. Find the volume of tap water necessary to cool the hot drink to 60 degrees Celsius, assuming no energy is lost to either evaporation or conduction. So we're looking for the volume of tap water necessary to cool the drink to 60 degrees Celsius, right? So, um, what do I want to say? I don't know why I'm blanking on this problem. Give me a sec here. Okay, so 15 degrees Celsius, you add that tap water. So that'll cool it down. Okay. So I think I understand what's going on here. So this is kind of like a transfer of energy in a sense, right? Basically what's going on here is that this is a concept where, if I remember this correctly, I hope I'm saying this right. I just haven't looked at this stuff in a while. But there should be a transfer of energy naturally from things that are hot to things that are cold, right? And if you remember from Gen Chem, like when you have that transfer of energy, like a release of energy from one object has to be an absorption of energy into another object, right? And so in that case, right, everything should end up at the end in an equilibrium kind of state where everything's kind of at the same temperature, right? So if we started off with this really hot drink at 80 degrees Celsius, we want to get it down to 60, and we add this extra water here, right? Then the coffee system, right, the coffee itself will have that final temperature of 60. At the same time, that water that we added will also end up being that temperature of 60, right? Because think about it, like I guess from a very informal, stupid kind of like way of thinking about things, like if you add some water or something, right? If you cool down your drink and you start drinking it, like it has a uniform temperature. Like you're not drinking 60 degrees of Celsius like in one spot and like 30 at another spot, right? So it all kind of ends up being the same at the end. So that's kind of that equilibrium state that you're looking at, where there's a transfer of energy, right? Heat is defined as a transfer of energy from hot to cold, right? From things that have a higher average kinetic energy, higher temperature, to a lower average kinetic energy, lower temperature, right? So whatever heat is lost from that really hot coffee at 80 degrees Celsius, or whatever energy is lost there, right? It's transferred as heat into the water, right? To bring it to a net or a neutral kind of state at 60 degrees Celsius. So it's like, all right, I have 80 degrees Celsius, right? Let me give you some degrees of mine cold water that we can come to an agreement at 60 degrees Celsius. That's kind of what's going on here, right? So 80 degrees Celsius, that hot coffee is going to be like, all right, well, I'll give you some of my energy to the cold water, as long as we both kind of come to that 60 degrees Celsius kind of state there, right? So there's a release or a transfer of energy, right, from that hot coffee to that cold water, right? And that kind of like change in energy there should be giving us that final temperature of 60 degrees Celsius, right? So if we look at decrease in the energy, right, of the coffee, or a release in energy from the coffee should equal the absorption of energy, right? Transfer of energy into the water. So like essentially what you say, like negative Q coffee equals positive Q, the amount of energy absorbed by the tap water, right? That's kind of the idea that's going on here. And so Q is equal to MC delta T, like we know. And so you can say that, okay, well, MC delta T here equals MC delta T there. Obviously, with this being a negative sign over here, right? And you can see that, all right, so we started off with 180 milliliters of water, right? And that's around 0.180 kilograms, because remember, 180 milliliters of water divided by 1,000 milliliters, kilograms on top. We already went over that conversion unit before. So 0.180 kilograms times the specific heat of water, which is 4,187 joules per kilogram Kelvin, and then times the change in temperature, right? So we want the water to go from 80 degrees Celsius to 60 degrees Celsius, right? Or we can say that it goes from 353 Kelvin to 333 Kelvin. So TF minus TI, we end up at 333 Kelvin, and we started off at 353 Kelvin, right? So that's a decrease there of negative 20, or a decrease of 20 or negative 20 there, right? On the other hand side here, we added some of the water. That's the mass that we're looking for. We don't know exactly how much. We can figure out a certain kilogram value, and from that kilogram value, we can convert that to milliliters, right, to volume. So we have this certain mass of water that we're adding. It's unknown. We know that it has 4,187 joules per kilogram Kelvin as its specific heat. And then we know that that water, like I said, they have to come to an agreement, of a final temperature. So they're like, all right, let's end up at 333 Kelvin. Let's agree to come to that 60 degrees Celsius final temperature, right? Make everything uniform. The water itself started out at 15 degrees Celsius, right? So that's around what? 288? Yeah, 288 Kelvin is where it started at. So you can see here that this is actually a positive change in temperature. It went from an initial of 288 Kelvin from 15 degrees Celsius to 333 Kelvin, 60 degrees Celsius. Came to that agreement. There's a release in energy from the coffee, transfer of energy from the coffee to the tap water. So there's a uniform temperature there that's more drinkable, right? Or easier to drink. So, yeah, if we go ahead and solve that, we should be able to get the mass of the tap water that should be added to come to that stable temperature of 60 degrees Celsius or 333 Kelvin, right? If we solve for that, and remember, we actually need a negative sign here as well. And the reason why is that, well, if we didn't have that negative sign, then this is a negative here, while this answer is a positive. You would have a negative equaling a positive, and you can't have that. And you would end up with a negative mass as your answer. That's not going to work out. That's why you must have one side being negative to indicate like a release of energy, and one side being positive to indicate a absorption of energy. And yeah, you can cancel out both C's because they're the exact same value. Don't make the mistake of plugging in the heat of vaporization here, which was that this value or this value. I think someone did that earlier. And the reason why is, like, at least from a conceptual standpoint, that's incorrect. What ends up happening is that you still do get the same exact answer because both sides will cancel out, even if you had that incorrect heat capacity there. The reason why I'm saying it's probably better to use, well, it's not probably better. You should use this, and this is correct, because the heat of vaporization, like I said, is only an indication of like the amount of energy that needs to be absorbed or released to only transfer between states of matter, go from liquid to a solid, solid to liquid, liquid to gas, gas to liquid, right? And not cause a change in temperature. Specific heat capacity, which is this value right here, the joules per kilogram Kelvin, is the amount of energy that you would need to absorb or release, right, to cause a change in temperature per kilogram of that specific substance, right? So even though you might get the same answer, just make sure to plug in the correct values because you might get a point off for that. Anyway, your mass that you end up with should be around, what is it? Like 0.08 kilograms, right? And that's around 80 grams if you multiply by 1,000. And then we know that 80 grams, well, 1 gram is 1 milliliter, so 80 milliliters. Anybody have any comment as to if this value is correct or not? Well, is it how confusing is it? Just curious. Like I have a section here that should be able to help with like navigating it, at least for beginners to using Discord. But I mean, yeah, I understand definitely like people are more familiar with Zoom and stuff like that, and I totally agree. Like, I mean, it took me a while to set up this thing, but um, I mean, I just think in the grand scheme of things, like it's not just about the sessions. It's also like getting help from other people too, and having it in a very organized manner. Like, unless you guys don't think this is helpful at all, like just tell me. Because I just hate group me how like everything is just kind of a mess. But yeah, like when I had Zoom, like 10 people would show up on average. Yeah, no, I totally agree. Like, yeah, I mean, hopefully, like the more you guys use it, um, it'll kind of get a little bit easier, and that's why, like, I had some people suggesting like some stuff last night about like organization for the server, and like at the moment, I think I'm probably just gonna keep things the same because I feel like it's probably more like overwhelming anyway. But like it's I guess good to have kind of some separation for the questions between like stuff about the written homework or the online or the labs and stuff like that. Yep. Mm-hmm. That was the temperature of the tap water, which was the 15 degrees Celsius. So I took 273 plus 15 degrees Celsius to get the temperature in Kelvin. But yeah, um, I think that's it for this session. Have some things to talk to you guys about, so just stay here for a sec. I'm just gonna end the recording so I can upload it in the background, so it's gets up on YouTube as soon as possible. But yeah, just give me 1 second. Please stay in the channel here. Just have some things to talk to you guys about.